Operations with complex numbers. Okay, so we've talked about how the square root of -1 is I. So then we can also say that if we took I squared, it equals -1. Well, why is that? Well, if I look up here in the top equation right here, if I decided to square both sides, then the square root and the squared symbol would cancel each other out, giving you -1 is now equal to I squared. Alright, so basically we need to do some work with I. So knowing that the square root of -1 is I, knowing that now -1 is I squared, we can further that understanding. So basically, we know this and we know that. So if we had I to the third, we can represent that using our multiplication and exponent rules, and we can take I squared, I to the first, add their exponents to give you that 3, but we know I squared equals -1, and we know that I gives you I, so therefore I to the third equals -I. We can do that same concept with I to the fourth. We have I squared and I squared. Well, we just said that I squared equals -1, and -1 times -1 gives us 1. And one more example with this is I to the fifth. Well, we just know that I to the fourth is 1. We just did that. And then I is I. So we get positive I. And that is the same thing as I to the first. So this pattern will repeat itself. Notice how I to the sixth is -1. And notice how I to the seventh is -I. And then we have I to the eighth is 1. So if I went I to the ninth, would you know what that was? I to the ninth would be I, and it would repeat itself over and over again. So we need to memorize this box right here, because after the fourth power, the pattern repeats itself. Okay, so now I can ask you the value of I to a crazy number. So we're going to use that pattern and break it down a little bit further. Now, this is the way that I break it down. It's not necessarily mathematical or math backed up. But if you see, we have 4 parts to the pattern. So we could say that this first one is the first out of 4. The second one is the second out of 4. The third out of 4. And this last one is the fourth one out of 4. Well, if we take that concept and let's just say we make them a decimal. Well, 1/4 as a decimal is 0.25. And 2/4 as a decimal is 0.5. 3/4 as a decimal is 0.75. And 4/4 as a decimal is 1.00. So basically, I could say, okay, well, -I is 3/4 the way through the pattern, okay? So what does that mean? Well, if I have I to the 24, I need to know how many times I'm going to cycle through that pattern. So I could count, and I could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and so on. And I'd go all the way up to 24, and 24 would be written down here. Meaning I'm going to go all the way through this cycle. Turns out it's going to be 6 times. So the answer to this is 1. Well, how would I know that? I am not going to expect you to write all of these crazy numbers over here. That's just nonsense. Okay? So what I do is in my calculator, a little trick would be 24 divided by 4, which gives you 6.00. And what I'm going to focus on is this part, which matches our 1.00 there. So that's how we know to look at I to the 4th, which is equal to 1. So I to the 24th is equivalent to I to the 4th. Okay, I want to clean some of this up over here. All right, so let's do it again. If I did 214 divided by 4 in my calculator, I'm going to get 53.5. Okay, so what that means is I'm going through this pattern 53 whole times, and then I'm stopping half of the way down. So I to the negative 14th is negative 1. I to the 9 would be 9 divided by 4. And if you plug that in your calculator, or if you just know it, 4 goes in 2 even times with a quarter left over. So we would cycle through this pattern 2 full times, right? Because we also know from the left, this is where we end. I to the 8th gives us 1, and then we have to finish 1 more to match at a quarter of the way down. So I to the 9th equals I. And then our last one, 39 divided by 4 gives me 9.75. So I can go through that cycle 9 times and 3/4 of the way down, which is going to allow me to say that I to the 39th is negative I. Okay, so why can we do this? Well, because I isn't just a variable. I is part of a complex number. So since we can evaluate I to the 1st, I to the 2nd, I to the 3rd, and I to the 4th, we can evaluate every value of I to any power. So if you notice, whenever you have an I, whether it be in your final answer, it is only going to be either an I, it's going to turn into a negative 1, it could be a negative I, or it's going to turn into a 1. So you can't have any I in your final answer that has an exponent greater than 1, because if you can, we can convert it into a numerical value or a numerical value of I. Okay, so moving on, and we're going to come back to that in a little. It is important that complex numbers have real and imaginary parts. And a whole complex number is a plus bi. So, what's the real part? Well, the real part is the number in front that is not included with I. So therefore, your complex part is that minus 2i and plus 3i. All right, so now we can add and subtract with complex numbers. So when we add and subtract with complex numbers, we add and subtract the real parts, and then we add and subtract the imaginary parts. So here are my real parts. 3 plus 4 equals 12. And then my imaginary parts are 2i and negative 5i, so I have minus 3i. And that is my final answer. All right, now at the bottom, be careful. The first thing we have to do, since it is subtracting a whole binomial, is distribute that negative. So the first thing I'm going to write is it properly distributed. So negative 4 plus 8i minus 6 plus 4i. Now we're going to identify the real and imaginary parts. So my real part here is negative 4 and negative 6. So I'm going to get negative 10. And then the imaginary part here is 8i and 4i. So I'm going to get plus 12i. So notice when I add, I still have all my final answers in terms of just I. So we can't have any exponent of I be greater than 1. And so far we're good. All right, now when we multiply complex numbers, we distribute. We treat it just like you would if I was considered a variable. So now what we do have to remember though is that I squared is -1, and you'll see where that comes into play. So the first one's kind of simple. We just take 2 and we distribute it. So we get 14 plus 18i. The second one we're distributing, but just with I. So we get -2i. The number goes in front as if it was a coefficient in a variable. And then we have -i times -5i. So first off, a negative times a negative is a positive. And then we have 5i squared. But remember, we know that I squared equals, or has a numerical value. So that equals -1. So I'm going to write out all my steps here. So it becomes 5 times -1. And the answer, so that becomes -5. And if you looked at the beginning, the real part goes in front. So now all of a sudden I have to switch the order. And I have -5 minus 2i as my final answer. So we had an I with an exponent greater than 1, so it converted into a numerical value of -1, and now our final answer is what we want it to look like. All right, if we have two binomials, we just double distribute them. So we get 15 plus 27i -35i and -63i squared. Okay, so there's two things that are going to happen. I'm going to combine these like terms, and then I'm going to make I squared -1. So I get 15 minus 8i minus 63 times -1. So that's going to turn into 15 minus 8i plus 63. So my final answer with the real part in front, and it must be in front, is 78 minus 8i. All right, let's look at another example. Again, we're going to double distribute. 2 times -1 is -2. 2 times 2i is plus 4i. 5i times -1 is minus 5i. And then 5i times 2i is plus 10i squared. So we get -4. I'm going to combine these two into minus I, and then I'm going to say plus 10 times -1, which once again, same beginning, but now we have minus 10. So my final answer is -12 minus I. So I understand you might not feel like you need to do every single one of those steps, but I also want to just add, and that's okay, but I also want to add that that's also where a lot of mistakes are made. So just be diligent if you're going to do some of that multiplying in your head. Okay, so the last concept today is the conjugate of a complex number, where the real part stays the same. Did you hear that? The real part stays the same. And the imaginary part becomes opposite. Opposite as in, if it's positive, it becomes negative. If it's negative, it becomes positive. All right, so I want the complex conjugate for these three examples. So the real part stays the same. So the real part, again, we need to know that's negative 3. So the conjugate is negative 3 because it stays the same. 4i is the imaginary part, and that becomes opposite. So it says plus 4i, so the conjugate is minus 4i. For the next one, 7 stays the same, that's our real part. Minus 2i is our imaginary, so now it's going to turn into plus 2i. Negative 3 is our real part in the third example. Minus 5i is going to become plus 5i. Notice how only one part, the imaginary part, changes. The rest stays the same. So let's take a look. If we multiply a complex number by its conjugate, like right here, what happens? Well, let's use our multiplication like we did before and see what happens. So we do 4 minus 10i plus 10i minus 25i squared. So this middle part, I'm going to add those like terms, but they're the same. So they're going to add to give me 0. But then I squared is negative 1. So my next step is 4 minus 25 times negative 1, which becomes 4 plus 25, and my final answer is 29. All right, another example that's a little simpler. 5i and 5i. When you have just, when we are going, okay, so when we, over here, let's look on this example. We have the conjugate, because the real part would then be positive. I'm sorry, positive 0, it would be 0. So 0 plus 5i, 0 minus 5i. And when you multiply them, you get negative 25i squared. Well, we know I squared is negative 1, so your answer is 25. So if I were to not think about conjugates, but just multiply two numbers with the i's together, and you'll see why that applies in a second, I'm going to get 25i squared, which is negative 25. Now, with these two examples, they are separate. I'm not trying to compare the 25 and negative 25. My goal here is to show you when we multiply a complex number by its conjugate, all the i's go away. They all cancel out. They all turn into negative 1, or they all add in a 0 pair. So notice how I had a bunch of i's at the beginning, but now I have 29, negative 25, and 25. So why do we care about that? Well, on this page, when we divide with complex numbers, there's a rule. We cannot have I in the denominator. So we're going to use the conjugate to get rid of that, because we know if I multiply it by the conjugate, all the i's cancel out. So that's what I want to do, since I don't want I in the denominator. So let's take a look at the first example. Now, you don't have to, for the first example, you can just multiply it by 3i. It doesn't have to be negative 3i. And that's just because you don't need to do the opposite here, because all you need really is I squared to be, is to cancel out. So we have times 3i over 3i. We have to multiply the top and the bottom by the same thing. You can't just choose one. I'm going to put parentheses in the numerator because I'm going to distribute. So I get, up top, I get 3i plus 6i squared all over 9i squared. So this simplifies into 3i minus 6y. Well, I squared equals negative 1. And then on the denominator, I'm going to get negative 9, because I squared equals negative 1. So 9 times negative 1 is negative 9, and 6 times negative 1 is negative 6. So now what we do is we simplify. So we have 3 goes in the 3 once. Oh, I actually need to write my real part first, so I'm going to do that. 3 goes in the negative 6 twice. And then 3 goes into 3i once. And 3 goes into negative 9, negative 3 times. So the proper form, we really don't like to have negatives on the denominator, so that negative is going to flip the top. So we're going to get actually 2 minus I over 3 as my final answer. Okay, so for the next one, we have a whole complex number with a real and imaginary part, unlike for our first example. So this one might make a little bit more sense to you. Now, you have to multiply the top and the bottom by the complex conjugate of the denominator. I don't care what the top is. I'm allowed to have i's on the top. So I'm going to multiply it by 2 plus 9i over 2 plus 9i. I'm going to put parentheses on everything. And then I'm going to distribute the numerator and the denominator. So I get 10i plus 45i squared all over 4 plus 18i minus 18i minus 81i squared. So I'm going to go back, and these I squareds are going to become negative 1, and then these two middle terms will actually cancel out, and that's what we noticed before, and that is our goal. So we get negative 45, because again I want the real part in front, plus 10i. It became negative because of this I squared. All over 4 plus 81. 81 became positive because of that I squared. So my final answer is negative 45 plus 10i all over 85. Well, these can all be simplified. 5 goes into all of these, so we have to simplify all three numbers into negative 9 plus 5i over 17. Two more. So I'm going to multiply this one by the conjugate of the denominator, 4 plus 5i All right, so I get 12 plus 15i plus 8i plus 10i squared all over 16. All right, so I know, because I did it correctly, and you should know by now and how to do it, that my middle two terms are going to cancel. So I'm not going to write 20i and negative 20i. I'm just going to go straight to negative 5i times positive 5i, which is negative 25i squared. You can always confirm to make sure you're correct, but I know that that's what should happen. So then I get 12 plus 23i minus 10 all over 16 plus 25. Those signs changed because we had a negative, or I'm sorry, we had an I squared, which equals negative 1. So my final answer is 2 plus 23i, remember real part in front, all over 41. This is the final answer because everything is as simplified as it could be. All right, last example for the day. I'm going to multiply by the conjugate. If you feel like you can do this on your own, start it or pause the video and then we can go from there. All right, so my numerator becomes 84 minus 108i minus 56i plus 72i squared, all over 49 minus 81i squared. That simplifies it into 12 minus 164i. So if you didn't get that, go back and check. Make sure you added your middle two terms correctly, and then 72i squared will become minus 72. And my denominator is 130. This can be simplified. Everything's divisible by 2. So we get 6 minus 82i all over 65 as the final answer.